Hello, my name is Albert Rajkumar, and I'll be talking about a testbed for gravity simulation platform in low Earth orbit that I did along with my co-author, Professor Olga Benova. So let's begin with the issue that inspired and drove this research. Now, I like to refer to this conceptual graph, which illustrates that there's a knowledge gap in our understanding of the human body's responses to long periods of exposure to partial gravity. And this is an issue that we should address if we want to ensure the safety of future lunar and Mars long-term missions. So how can we go about building a bridge over this knowledge gap? Well, a major area of artificial gravity application has been into mitigating the negative effects of microgravity on crew. With this proposal, we're exploring how artificial gravity can help test and evaluate human and engineering systems under partial gravity conditions. And so, to take this paradigm forward, we need to develop a new breed of research facilities which provides partial gravity for long periods of time and which is outside the confines of Earth's gravity. And so the end goal is to develop and operate a variable gravity research platform in low Earth orbit as shown in box number 3. But to get there, we are adopting a phased approach. And so the next logical step after our Earth-based centrifuges is a testbed for the said research platform, and that today is the focus of our study. Now this testbed, it consists of 2 Crew Dragons with most of its internal outfittings removed and converted into the lab. They are tethered to a central hub which consists of the Progress MS and Pritchell module. Now the intent is to capitalize on the pre-existing capabilities of the International Space Station to support the testbed and take part in the commercialization of low Earth orbit. And to minimize the research and development time and cost, we are proposing the use of off-the-shelf components as much as possible. Now, to give you a summary of how the testbed will function, it will first undock from the International Space Station and it will move to its test operation zone. There, it will spin up and perform its test operations. After that, it spins down and docks back to the International Space Station and the cycle repeats. Now, 2 sets of test objectives were identified, technical and physiological. Today in this presentation, our focus will be on the physiological test objectives. They include testing for response to Coriolis forces, testing for response to different levels of gravity, and testing response to different rates of angular velocity and radii. Now, before we go into the experiments to address these test objectives, let's see what historical precedents that we looked at and took inspiration from. We primarily looked at ground-based centrifuge studies that were conducted by NASA and ESA, but we specifically identified a study done by James Lackner and Paul Dizio in the spinning room, as you can see here. Now, our intent is to study the experiments conducted in this case study, take them as reference experiments, and see how we can adapt these experiments for our testbed in low Earth orbit. And so the first experiment is one where the objective is to check for accuracy in pointing to targets in a spinning environment. The task was to extend the right hand forward and location of a just extinguished visual target in darkness. The experiment was set up in such a way that the room was conducted in a dark room, and when the subject lifted his or her finger from a start button to point, the target was extinguished. Thus, the subject reached without receiving any visual feedback about movement accuracy. Now, as for result documentation, the figure here shows the top view of the hand movement on top and the deviation from baseline during and after rotation on the bottom. Now this can serve as a framework for our recording of data of the experiments in the testbed. Similarly, 3 other experiments were identified which dealt with checking for intermanual transfer of adaptation in reference 2, adaptation of leg movements in reference 3, as well as adaptation of head movements in reference 4. Now, let's look at how these reference experiments can be adapted to be performed on the testbed. The first experiment, it retains the same task and objective, which is to check for accuracy of pointing the targets. Now, it can be set up in such a way that the subject is sat on a chair with his arms on an armrest. Now, when the subject lifts his or her finger from a release trigger on the armrest, the target on the screen will be extinguished. The subject attempts to place his or her finger on the recently extinguished target, and motion trackers can track the fingertip location throughout this time period at 100 Hz. And the sequence can be repeated as many times as necessary. Experiment number 2 also retains the same task and objective of its reference experiment, which is to check for transfer of adaptation achieved from one arm to the other. Now for this, we can set up the experiment very similar to the previous experiment, but with a set of one hand first and a set of the other hand second to check for transfer of adaptation. And experiment 3 aims to study the adaptation of Coriolis force perturbations of the leg movements. Now the task is to stand and kick with the leg at a visual target while the head and waist are stabilized. Please feel free to pause the video and read the setup and documentation and results if you wish. And lastly, the experiment number 4 will study the adaptation of Coriolis forces perturbations of head movements. Now specifically pitch movements of the head while the subject is sat on a chair. Okay, now let's see what the interior of the test bed might look like in order to accommodate these experiments that we just discussed. Over here on the left hand side, we can see the kind of volume of space that we can expect in a Crew Dragon with its internal outfittings removed. And on the right hand side is the interior of a mock-up of a Crew Dragon, which gives us a good visual cue on the volume of the interior. Now this is a conceptual sketch of the elements inside the testbed, where we would need cameras and motion tracking system running around in the circumference of the experiment zone to fully capture the movement of the subjects. We would also need markers which indicate the direction of spin in case we want to expand our experiments. And finally, the station itself, comprising of a screen on a table and harnessing mechanism which can serve both as a chair and a standing harness. We also conducted some anthropometric studies and overlaid them on the expected volume, and it seems to be more than enough for the simple non-translational experiments like the ones proposed. Now before we wrap up, let's talk about the concept of operations, the concept of test operations rather for this test bed. It's categorized into technical and physiological, but for this presentation, we will again be focusing on the physiological test operations. Now, a test operation will include variables like the experiment being conducted, the rate of spin, the radius of spin, the gravity level generated, and the duration of spin. Now, in the case of physiological test operation P1, we see that it accommodates the experiment P1 of pointing at targets at an RPM of 10 and a radius of 9.5 meters. The test operation P2 can run the same experiment but on a lower RPM and higher radius of spin, resulting in the same simulated gravity. P3 and P4, etc. can continue changing these variables to achieve the different test objectives that we had identified earlier. And so in conclusion, the anthropometric study suggests that the customized Crew Dragon can accommodate the proposed experiments, and this testbed could be a way to bridge the knowledge gap and make our future missions in deep space safer. And it can be done in a relatively low-cost manner while taking advantage of the International Space Station and commercialization of LEO. And with that, we thank you for your attention, and this has been our presentation on a testbed for gravity simulation platform in low Earth orbit. Thank you.